Okay, everyone, let's take a look at Module 26202-23, Motor Theories and Application in the NCCER 11th edition. This will be Section 1.00, DC Motor Operation. Compatible electrical power circuits are used to power and control motors. These circuits provide electrical current and protection from adverse conditions. When magnetic material is given an induced magnetic charge, a field of magnetic force is developed. Magnetic lines of force are continuous and they form closed loops and they do not cross. Magnetic lines of force with polarities in opposite directions tend to attract, and those in the same direction tend to repel. The armature is a movable electromagnet located between the poles of a fixed magnet. When the magnetic field from the armature conductors interacts with the magnetic field from the fixed magnet, motor rotation occurs. If two fields are not in the same plane, they cannot affect each other. A practical motor must develop torque to exhibit continuous rotary motion. Torque is produced by mounting a loop in a fixed magnetic field. Current is applied, which causes the loop to act like a lever. Larger armatures produce greater torque. In the absence of enough torque, a motor stalls. A commutator reverses the direction of current through the armature for every 180 degrees of revolution. To produce a self-starting motor, additional coils are wound on the armature and more commutator segments are used. When the loop is perpendicular to the field, the interaction of the magnetic field stops and the neutral plane is reached. No torque is produced in the neutral plane. Because the magnet's field direction remains the same, the field interaction after commutation keeps the torque going and maintains continuous rotation. Elementary DC motors operate erratically and produce torque irregularly. Building an armature with two or more loops placed at right angles sets up two parallel loop circuits. The two-loop system is self-starting and develops steadier and stronger torque. Armature reaction is caused by the interaction between the main magnetic field and the magnetic field produced by the armature. The amount of armature reaction determines how far the neutral plane is shifted. Commutation must occur at the neutral plane or it will draw an arc. The armature reaction can be overcome by installing interpole windings. An operating DC motor acts like a DC generator. Battery voltage and CEMF are opposite in polarity. Because CEMF, or counter-electromotive force, is not as large as externally applied voltage, it cancels not only part of the applied voltage. The CEMF value depends on field strength and armature speed. CEMF acts as a load for the DC power supply and limits the amount of current the motor draws. If the armature stalls and no CEMF is produced, the motor heats up. CEMF is present in all motors and is necessary for operation. Large DC motors require a starting resistance inserted in series with the motor armature. Without a starting resistance, the starting current would be abnormally high. If the starting resistance is not used, the value of armature current can be found with this equation, and after starting, external resistance can be removed. To find series resistance at the moment of motor start, use this equation. Two types of DC motors connections are in common use: series motors and shunt motors. When an external load is applied to a shunt motor, it slows down. The speed remains constant as long as the load is constant. The current amount through the armature depends on the load. The main advantage is that rotational speed remains fairly constant. The main disadvantage is that the motor does not develop much torque when first started. Remember, operating characteristics must be matched to the application. Warning: never open the shunt field circuit of a DC motor when the motor is operating, especially when unloaded. An open field may cause the motor to rotate at a dangerously high speed. Large DC shunt motors have a field rheostat with no field release feature that disconnects the motor from the power source if the field circuit opens. The field coils of a series DC motor are connected in series with the armature. As the motor speeds up, armature and field current decrease. Series motors are not belt connected to their loads. Series motors are good when there is a wide variation in torque and speed requirements. Compound motors, applications that require high starting torque and constant speed under load, are ideal for compound motors. Compound DC motors have a normal shunt winding and a series winding on each field pole. They may be connected by a long or short shunt. And some trade terms you should read over and become familiar with for this section. And some review questions for this section. It says, when studying operation of electric motors, it is important to remember that magnetic lines of force form infinite straight lines, do not cross, attract materials with the same polarity, pass through conductive materials, and I'm going to say do not cross. A motor with the field coils connected in parallel with the rotor winding is a shielded motor, a series motor, a shunt motor, or a sealed motor. I'm going to go with shunt motor. All right, everyone, that's it for that section. The next section will be 2.00 AC motor operation, and I will see you over there.